Excellent. Okay. So I'm the founder and CEO of Body Rocket. We are a Brighton-based company. We've been located out of the Fusebox for very close to 4 years now. It's been a fantastic incubator for ourselves as well as many other tech companies in the Brighton area. And that's located in the New England house, if you're not familiar with the Fusebox. And over that time, we have really been an R&D company, building out the necessary technology to do real-time aerodynamic drag measurement. And it's quite a complex product, and we really needed to build out several new technologies just to make that happen. The team that we've built reflects that. It's a very broad set of skills. I've never been around so many smart people at the same time, so it makes for a really great place to work, as long as you like geeky jokes. We've grown remotely, so not everyone is based in Brighton, but we are proud to be part of the Brighton startup community, and I find it a really great place to meet and innovate. Myself, in addition to founding Body Rocket, I'm a former elite athlete and represented the U.S. At the 2004 Athens Paralympic Games, where I was a pilot with a blind athlete on the sprint tandem, and did various other things in the cycling world. Most of my career has been in the cycling industry. I started with companies like Trek Bikes and PowerTap and Cyclops before coming to the UK. The rest of the smart team that surrounds me has just a really fantastic array of backgrounds, from our CTO, Neil Newell, who has done everything from the motion control rig on for the flying scenes in the 1980s Superman movies to data companies, and he was just telling me a few days ago they actually did. Oh, I'm gonna screw it up now. I forgot my anecdote here. They did all the data aggregation for one of the live shows where you would vote on TV. And since I just don't watch TV, I'm gonna whiff on this one. So we'll carry on to Anna, who's joining today and is the core and entirety of our data team right now. And she comes to us from a background in astrophysics. It just brings an amazing skill set in terms of finding the signal in the noise in the data that we have. Our mechanical engineer also comes with a very, very interesting background in that before he came to us, he was training to be a pilot in the Royal Navy. And we won out over that somehow. Our embedded software developer also comes from the same industry. There's been people for the last 10 years or so trying to get real-time aerodynamic drag measurement, and he was one of the founders of an early company doing that, and also happens to have a telescope named after him. And finally, Keith Wakeham is an expert in load cells, which is really the foundation of what we're doing, and all those things have been really, really important to build the technology that we need. And we're at the point now where we are looking to add a whole new aspect of not just one or two bikes and this growing data set on that, but now tens and hundreds of bikes. And it didn't take us to get to more than 2 bikes to realize that was going to be a really big challenge, and we needed to address the problem as quickly as possible. So what are we doing? We're measuring aerodynamic drag on a bicycle. And so for most of the history of cycling, aerodynamics has been something that you just had a feel for and you guessed about. And because of that, it didn't really become something that people spent a lot of time perfecting. About 20 years ago, that changed. People started going into the wind tunnel. Professionals started going into the wind tunnel. And in the last 10 years or so, companies have realized that there's money here. And if they can get a product out there, it's something that the consumers will appreciate and value. They've all been built on a technology, the same technology that hasn't been working out so far. We're coming at it from a very different approach and a very scientific approach. So what is the problem? Aerodynamics is the problem, and it's the problem because it's about 80% of everything that a cyclist is pushing against. And then in that, about 80% of that is the athlete themselves. And so while wind tunnels have been fantastic for bikes and wheels, they're much like a car or an airplane. You can design one and then with confidence go and make thousands and expect they're all going to work the same. Bodies are different, we're all shaped differently. And so the solution has been to put everybody in the wind tunnel for the last 20 years at the professional level. Again, it's very expensive to go into a wind tunnel. And that's not really even a good solution because we change our positions as we're on the bike and as we go up a hill or go over a rough road. And so those have been points in time, and we really need a different solution. The sports tech wave that is bringing analytics across all sports, this is really the biggest application in cycling. If we can monitor an athlete's drag and improve it and give them feedback on that, it has the huge potential for gains in their performance. So our product, as I said, we actually are coming at this from a measurement standpoint. And so we've essentially taken the measurement device in a wind tunnel, which we call the wind tunnel balance, and integrated it into the bike itself, along with wind speed measurement and the rest of the environmental measurements that you need to get to a coefficient of drag, which is the parameter that people look at when trying to understand their aerodynamics. The research on this is still very preliminary, but some research that came out this year from the University of Antwerp shows that just simply knowing that what your CDA is in real time allows you to adjust your position and maintain it to the point where you're getting 1.5 to 3% gains. In a sport where, like most sports, a 0.5% gain or a couple tenths of a percent will be the difference between first and not being on the podium. On top of that, the professionals that have been going into the wind tunnel, or anybody who's going into the wind tunnel for the first time, it's fairly broadly acknowledged that you can expect to see gains of 5% or even greater. So when you put those together, we're talking about being able to take a sort of mid-pack athlete right now and make them someone who is competing for the win, which is pretty exciting and a really big difference in terms of what we can do for athletes. So how does it work? A lot of this I'm going to leave to Anna, but in terms of what we're collecting and gathering on the bike, we have essentially four sensors that are the handlebar, the saddle, and the two pedals, and then we're measuring wind speed and the rest of the parameters, as I mentioned, that will get you to a calculation for a coefficient of drag. Those all come together, and I guess the best way to explain this is if you sit on a bike, well, from a physics standpoint, if you sit on a bike and you're not moving, all those forces in the horizontal should sum out to nothing. And that is, in fact, what happens on our system. And it's only when you put an external force like a wind that you measure something. And so the summation of those forces at those 4 points ends up being your aerodynamic drag. And that's really the heart and core of our system. That goes live to a Garmin or other cycle computer on your handlebar and gives that live feedback. But a lot of the power in this is being able to look at your progress over time and be able to do batches of tests, and then to be able to look at that data in hindsight and understand what you've done and what effect it's had, your ability to maintain aerodynamics over the course of the race. Races might be different lengths. You may be able to maintain one position for 5 minutes, but different for 20 or 30 minutes. And right now there's no visibility or insight of that. And that's something that we need to be able to bring out to the athletes. So where are we at in this journey? We've validated everything in the wind tunnel, and we are currently out on the road and doing testing. We're starting to engage with professional teams, as well as academic institutions. I should mention that's something that's quite exciting about where we're going with this is we have a very strong response both from research and from professionals. Professionals obviously have something to gain from this, but researchers are looking at this and saying this is a brand new data set. There's a lot of groundbreaking research that can be done here. And so we have the privilege of being able to engage with institutions and very bright people at universities around the world and collaborate with them on what this data means and how we can use it. We've started the design of that final product, and over this next year, that's where we're going to be going is to the preparation for the launch of a consumer product. But we're at that stage where we're now growing our fleet of bicycles, and we know that it's going to get very confusing very quickly, and we won't even be able to start to mine those larger data sets unless we have the ability to organize them and then really dig into them and understand them quite a bit better. So with that, I'll hand over to Anna, who can do a much better job of digging into the actual technical challenge we have with the data sets that we have.
Yes, thank you, Eric. Let me quickly share my screen. How is this coming? Oh.
It's good, but not full screen. There we go.
Yeah. So as Oscar mentioned at the beginning, this will be an interactive discussion of how we should better handle our data if you want, or how we should store it and manipulate it at the end of the process. So what I want to do now is to guide you broadly on how we handle and store data with our body rocket device. As Eric has mentioned in the introduction, we are measuring, collecting data from 5 sensors, which are located in 4 positions on the bike. So this is near the saddle, the handlebar, and the pedals. And each sensor comes with its own data stream. And we have a software that we developed at Body Rocket that aggregates all of these data streams, but not only aggregates the data, it also calculates the relevant parameters that we need to know for obtaining at the end drag measurements. This software on a standard training session runs live on our onboard computer. And as Eric has mentioned in the introduction, is sending real-time data to a Garmin device. And this enables the user to monitor their performance and adjust their position to obviously improve their aerodynamic performance. During the ride, the data is also stored locally in our onboard computer, but what we want is that at the end, it gets sent to a database via iOS or an Android app or anything that we have on the phone of the user. So this is, broadly speaking, what happens when the device is on the bike and when the rider is on the bike. But I want to give you a bit more details of the actual data that we are storing and how they are, broadly speaking, used. So both the raw sensors data and these high-level measurements, which do include drag, power, and weight, come in the form of high-frequency time series. So you can think of them as time series. And we thought of 2 different options that we could have to store this data on a database. So I'll briefly touch on both. In the option number 1, which is what I'm showing here, we could upload both the eye level measurements and the raw sensor data right at the end of the ride. The user will have immediately access and always access to these high level measurements, but we will also be saving the raw data. But in this case, this raw data will be kept cold, let's say, so there will be only accessed for backup or development purposes, so will not be needed to be frequently accessed neither by the user nor the analytical tools. Option number 2, which we would like to hear your opinion about, we could decide to only load the raw data to the database and have the high-level data be calculated on demand whenever required by the user or us. Either option, I don't think they change the philosophy of how this database needs to be accessed, which is the user only needs to see the high-level measurement, drag, power, and all the other parameters that we is interested in displaying. The raw data is kept for the algorithms or for us. I think it's the frequency of access to the raw data that will change in these 2 different options. So these time series are obviously capturing the dynamic part of our sensor. So they're capturing what's happening on the ride, but we also need to record sensor property infos. So these will be tables that enable us to identify each sensor and their performance. So they will contain things like the serial number, but also a set of parameters that describes the sensor performance as it comes out of manufacturing, if you want. They will also need to include properties that are, I would say, user and bike specific. So these will be properties that have to do with how these sensors are mounted on each user's bike. And also we would like to keep an eye on sensor diagnostic measurements. So this sensor info will also contain diagnostics of how the sensor is performing over time. Once this data is saved, it's relatively static, I would say, so it doesn't need to be updated very often, but there could be occasions when these updates or upserts will be needed. If this happens, and in any case, anytime that we need to reanalyze any historical data, it is necessary that we reassociate the sensor property info with a given ride and a given date. Okay, so moving into the layer that is most interesting to the user itself, obviously what we want to capture is also any information that can characterize a given ride. So we will have tables that contain things like date, user ID, location from GPS coordinates. We will like the user to be able to upload key features of a given ride, say specifying what type of equipment they were wearing on that given ride, if they had a given jersey or helmets and so on. But we'd also like to include any high-level statistics or summary that is useful for the athlete to understand their performance. So this will be the high-level summary of a given ride. So in terms of how we envisage the database to be used, we can think of two broad cases. There is the standard user and us as a company. The standard user is obviously performance oriented. And what they would want to do is access all the historical data to monitor their performance and how that has improved over time. So use cases of the database will be things like obviously displaying single rides, but also combine different rides by given keywords, say comparing rides that were done under using the same helmet, or comparing rides uphill or downhill, having weekly summary or monthly summary, and so on. For us as a company, we would like to do all of what I mentioned before, but we also would like to have the possibility to search the data on a more fundamental level. So going back to the raw data, to each of the individual columns in the raw data, you can think these are roughly 60 data entries. Look for sensor IDs, search the database for a range of values in a given parameter. The idea behind this is obviously, together with monitoring athlete performance, is also R&D oriented. So we might want to combine multiple rides or athletes to gain more insights on how the sensors are working, applying any machine learning algorithms that we want on the data, or monitor the sensor performance over time. In terms of the technical requirements for what we think our database will be, we are not in the regime of big data as you would think about it, but the data does have some volume. So we can think the training session lengths will be anywhere from an hour to a full day of training. So let's say 8 hours or so. 1 hour of training is about 300 megabytes of data. So yeah, you can think that a yearly volume for a single rider to be in the order of 100 gigabytes, and depending on how many sensors we will have out, and obviously for how long they record, the initial entire volume will be in the order of 100 terabytes of data, yeah, for a given year. In terms of frequency and level of updates for our database, the raw data obviously should almost never be updated. As I mentioned before, sensor properties and the high level measurement should not need frequent updates. If that happens, it requires going back and accessing the raw data. And obviously, all the info and the statistics and the analysis we perform, this will grow as the data grows over the year. In terms of latency, the strength of Body Rocket is obviously being able to display the drag measurement live on the bike. So this is taken care by our device, so the computer we have on board. Having said that, we would like that the user can get off of the bike and have access to the data that was gathered fairly quickly. So a few lag seconds is acceptable between recording all the entire training session and having it on a database, but yeah, we would like to keep this to a minimum. And in terms of security level, I think this is all pretty standard. We would want general data protection for the users, enable only authorized users to see the raw data, any algorithms that we have, and also monitor any activity that is going on in the secure access areas. So yeah, this, as you have guessed, we are just now starting thinking about how to put up a database for Body Rocket. And that's the reason why we are here. So I think we missed a little bit of the in-house knowledge about this. So we are really open to suggestions on how we should deal with our data streams that will be coming soon from several devices being on at the same time. So we are here to discuss with all of you, share knowledge of what we should be doing. And Oscar has volunteered to come up with a suggestion for this, which I think he would explain now.
I will caveat that I am coming to this as a data scientist and not a data engineer, but I've seen a data engineer, I know some, and so I've picked up some of what they're talking about. But those of you with greater experience in the audience will quickly spot this as an outsider's attempt. So the interpretation that I have of their challenge is from the user's data capture and collection. We'll need to send the data into some cloud-based storage to ingest it into a data warehouse to compute metrics from it, and then feed that data into a front-end dashboard app, as is very classic. The little bit of inside information I have is that Body Rocket already uses AWS cloud services for other purposes. So and then that's where my experience lies as well. So I'm building the following up on those technologies. So from the structure being from device, mobile, web app, and down into some object storage system, here's sort of a proposed structure. Object by object storage system in AWS, that means S3, analytics data warehouse being Redshift, and then you can picture orchestrating the ETL/ELT, it's kind of on the boundary, with Airflow and dbt. The data warehouse primary function will be to collect and develop user write and sensor data ingested from the app. But since it's such a flexible platform, it can also accept data from other source systems like accounting or CRM and the like. And so merging these composite data products in data warehouse is a possibility and will probably be a necessity going forward. But in what follows, we're going to focus on the device uploaded data that Anna was talking about. And this is the largest in volume, although not necessarily the largest in complexity. The web app needs to land this writes data into S3. And that's already within the organization's virtual private cloud, and that's where the data stays until it's shared at the bottom end. I picture that the paths or the file names on S3 include the user ID type dates and date or timestamp, or as well as other sort of data specific distribution keys. After a period to be determined, a copy of the full history of the raw data can be shifted from this hot storage S3 to a cold storage like AWS Glacier, keeping the raw data always available should the data warehouse need to be rebuilt from raw, or whenever the business logic or the translation from raw data to drag coefficients, if that changes, you may want to rerun the ingestion. Then you have that at all times in cold storage. This is a sort of overview of the data tables. You have some write properties that describe a single write. You have sensor readings describing a single tick of the clock. The data is collected at 100 hertz. So this is the largest table. The sensor readouts, what was it, 58 of them? And there's the sensor status variable that you can check for reliability of the data. Auxiliary data from other applications from the mobile device, like the weather info, mobile device type, etc., and of course the GPS, and then various updates that the user may want to push to their account, like their username, email, profile picture. And then finally, gear updates. As you create your profile, you can attach gear that you'll be using on each of the rides, because you will want to compare the coefficients of drag when you're wearing that helmet or that jersey or those shoes. The next step is ingestion of these raw tables into the data warehouse. And here the AWS Redshift working with AWS S3 works pretty well in parallel, so long as the distribution keys are coordinated to make that efficient. But in there is the analytics data warehouse. It includes a set of organizational schemas and procedures for migrating data from raw and to presentation. This is not a streaming data solution. It's updated on schedule with batch jobs. So the frequency of these uploads, that needs to be, Anna mentioned that it would be nice to have that in a number of seconds. You uploaded your one ride gigabyte. You'd like to see that at your front-end web app in not very long. Well, the frequency of that wait time and versus the there's a balance to be struck here between the higher frequency upload and budget for resources. But as the writer gets their drag force computation result displayed on device in real time, so that's collected on device, we figured we could stretch that time before the whole raw data is fully processed. So there may be a bifurcation where higher level data products are pushed in faster, and full storage and full working with the raw data is slower. The landing schema, this is the layer where the raw data files land, and this is only a limited history. So all data, once it's been propagated further down, is routinely purged from this layer automatically. The staging schema contains cleaned and processed data picked up from the landing layer. And here the data cleaning and filtering has been applied. Joins have been made from tables between different sources, and data type changes, specific data definitions. They've been brought into the raw data, into the format that is going to be used in the future layers. Now this layer also runs data quality checks and corrections handling nulls and missing data, duplicate rows, erroneous values, flagging possible concerns. Like the landing schema, the staging schema only keeps a limited history of the data in flight. Depending on the volume, the data can be routinely purged from this layer after it's been inserted into its destination tables, which are here in the analytics schema. This layer contains a full history of the properly formatted input data, as well as a range of business-facing data products. And these are these computed outputs, including from the proprietary algorithm that computes the drag forces, contains various aggregations, pre-computed analytics, and performance indicators, etc. And just in the analytics schema, you'll find a bunch of tables. There'll be dimensions, facts, data products, lookup tables, various other things. The dimensions, there are tables for collecting properties that apply to a set of observations, like the rides describes a whole bunch of these sensor measurements. So each row in a dimension table describes one owner of the given properties. Now, dimension tables are generally smaller, less frequently changed. Changes can be inserts or updates. And in contrast, the fact tables contain observations. And they're generally larger tables with that grow frequently with fresh inserts, but are rarely updated. That is to say, each entry is rarely updated. And then the analytics schema has the organization's specific business logic applied and contains digestible outputs for reporting and for exploring. Here's where you'll be connecting your collaborating or your partnering research institutions that want to do some scientific exploration into the drag force and rider data. And there may be some additional transformations that need to be made to prepare the data into a format for consumption by some specialized endpoints. That kind of format may not be useful for your analytics. Now, so that's the kind of draft version of our skeleton, or so to speak, of a pipeline, data pipeline. There are a bunch of considerations, and now I've been talking too long and wanted this to go faster. But if you think about these points as I'm opening up the mic on the floor, delivery. What is the best way to get the data off the sensor device and mobile device onwards into the cloud-based object storage? And cadence, how soon after a ride, or after a ride, should the data be served to a front end? And what is the impact of this kind of pipeline versus some other kind of pipelines, Kafka streaming, for that purpose? Compliance, privacy and personal information, obviously. Are there some other considerations involved? For instance, if health data is involved, heart rate monitoring and things like that. Security, safety against bad actors. You have your customer information, you have your proprietary algorithm, you just don't want the functionality to be compromised. And then there's the science, the having a good enough platform for these relationship explorations and causal investigation, data science, and actual physiological science that your partners are interested in.